So we are going to the third block now, and I'm giving up my chair seat here. So I think Dylan Rankin, are you chair?
Yes, that's right.
Okay, cool. I give the word to you.
Thanks. Yeah, so as Andreas said, we're moving to the HEP block of the poster session. And the first presenter will be Florian Rehm, who's a doctoral student at CERN. So Florian, if you want to share your slides.
So welcome to my poster presentation about reduced precision strategies for deep learning with a generative adversarial network use case from high energy physics. This work was done from CERN in collaboration with Intel. So I will first start with some background. At the Large Hadron Collider, or LHC, we have detectors to dedicate events like particle collisions. A part of these detectors are calorimeters. Calorimeters measure the energy of particles while creating a shower of secondary particles, like shown in this image. The primary particles enters from the left and the shower is developing in the detector. The recent GN4 simulation uses 50% of the worldwide LHC computing grid. Therefore, is intense research ongoing to replace the GN4 simulation by faster methods. The difficulty for searching an alternative simulation approach is that it must be the same level of accuracy in order to interpret the physical results. The approach of our choice are generative adversarial networks, or short GANs. Our GAN consists of two deep convolutional neural networks, and the very interesting thing is that we could come up with a neural network architecture which uses just 2D convolutional layers to represent the three-dimensional images. So in the research, we study the effects of quantizing our trained deep generator network. Quantization means simply to convert the numbers and weights and the numbers of the weights and activations of our neural network down to lower precision. The default precision in deep learning is floating point 32, which we quantize down to integer 8. The tool which we use for quantization is the Intel Low Precision Optimization Tool, or short ILOT. It works in an iterative process in which it quantizes some parameters of the model to a lower precision and prunes also prunes unimportant nodes of the neural network. It calculates an accuracy value and generates the next configuration of the parameters if the accuracy value is not good enough. This process is repeated until a certain level of accuracy is reached, and then we get our quantized model. So let's now look at the results of our quantized model. We start with the computational evaluation. In the graph, we can see that we get with the initial not quantized GAN model already a speed up of 39,000 compared to GN4. And with our quantized ILOT model, we get even a speed up of 67,000 compared to GN4. So this means in total a speed up of 1.7 due to quantization. On the right, we can see the times in percentage which are needed for specific parts of our model. We hope to get in future an even higher speed up when we fuse the convolutional 2D layer with the Liquirello function together with the batch normalization, and this should be supported in the next release of the ILOT tool. And due to quantization, we have to quantize the input data from floating point 32 to integer 8 at the beginning of our model, and we have to dequantize the output data from integer 8 to floating point 32 at the end of our model. And these processes alone cost us already around 20% of our computation time. So next, we check the physics results of our quantized model. We have two metrics to evaluate our generated images. First, we look at the uncertainty value. This is in the table here. The uncertainty value is calculated by taking the mean squared error between the 2D projections of our generated images in respect to GN4. We can see that the quantized ILOT model reaches even a better accuracy as the initial not quantized floating point 32 GAN model. This is due to the fact that we use this matrix also for optimization in the ILOT tool at the beginning. And we use the same model quantized with the TensorFlow Lite library as reference model And we can see that the uncertainty of the TensorFlow Lite models are worse than the iLOT model. And this effect we can see even better if we look at our second matrix, the shower shapes plots. We can see that the iLOT model in pink is very close to the GN4 data in red, which is the reference data. And the quantized TensorFlow Lite models are especially for the low energies in the left and on the right, very off. So to conclude, our GAN models speed up the calorimeter simulations already by orders of magnitude. And with our quantized iLOT model, we gained even a speed up of 67,000 compared to GN4 simulations while maintaining the physics accuracy. Okay, thank you for your attention and for organizing this event and for inviting me.
Okay, thanks, Florian. So as with the other sessions, we'll hold our questions till the end, and we'll move to Rui Zhang, who's a postdoc at University of Wisconsin-Madison.
Okay, so today I'm going to talk about hyperparameter optimization for machine learning using grid computing and HPC. This work is done in Atlas experiment. So I don't have to emphasize on the importance of hyperparameter optimization for machine learning. In fact, it is a very computing intensive task. So we would like to provide a service for the Atlas users to use the grid resources to run the hyperparameter optimization task. So the basic workflow is illustrated in this diagram. So we started with this starting button, which is the ask step. So we do ask step to ask for a hyperparameter point from the predefined hyperparameter predefined search space. Then with this point, the workflow basically will launch a steering container to run on the central service, which is can be one service or server, can be one local batch system. And this steering is encapsulated in a container, which I will talk about later. Later on, this steering container will generate a job based on this point, and then automatically submit to Atlas Grid site. Then the job will arrive to the grid site, and it will launch another container called evaluation container, and the user training jobs will be inside this evaluation container. So with this given point, the user job will be running. And then after this job finish, it will report back some metrics. It could be some validation loss or some AUC values. So this will, and then you can basically generate new points based on the old knowledge. So you do this loop until something is satisfied. So there are two essential components. One is the steering container, which is defined by, which can generate hyperparameters based on a search space. So this is a one container for all the users because the algorithms are basically shared by all the users. And we do support a lot of optimization algorithms. We don't specific any particular optimization algorithm, so users can choose as they need it. And the thing they need to provide is only the search space definition. Another container is the evaluation container, which run the user job. So this will run on the grid site, and this is fully user customizable. They can put whatever they want inside, but they don't need to put data because everything is run on Atlas data, and you can easily get the Atlas data from the Atlas grid. So, so we also implemented checkpointing. This is for some sites which has short war time. If the training job is longer than the war time, it will be killed in the middle. And the workflow will periodically upload checkpoints to grid. And if the job is killed, it will automatically retry. And during the retrying stage, it will download the checkpoint, and the training job will continue from the checkpoint. So we have several ongoing development. For example, to support some multi-architecture, in particular PowerPC as Summit. And we also plan to migrate image from Docker Hub to CVMFS or GitLab CI. And we are working for supporting visualization via Atlas Panda system. Although we do have an internal visualization tool, but it would be good to have a centralized visualization system. That's all from my side.
Thanks. Okay, and then finally, we move on to Charanjit Khosa, who's a postdoctoral fellow at the University of Genova in Italy.
Hello, everyone. I'm a postdoctoral fellow at the University of Genova. I'm going to talk about a new machine learning-based anomaly detection method named Anomaly Awareness. I did this work in collaboration with Veronica Sanz. I will discuss how this method could be used for the BSM searches at the LHC. Starting from the method, this method is based on the task of classifying the normal events, in this case the standard model events, while being made aware of the possibilities of the anomalies. And once the learning is complete, it is able to detect the unseen anomalies. The way this method works, it has two parts. First one is the prior run, and second one is the anomaly detection run. In the prior run, we perform the basic classification for the normal data set, and this run decides the model architecture and all the hyperparameter. And once we have a model, and then we, in addition to the normal data set, we also load the anomaly data set, and we calculate the entropy loss for the normal examples as well as for the anomaly examples. The important point is that for the anomaly examples, we consider the uniform distribution over all the classes in the normal data set, and we perform the training for the pre-decided number of epochs from the prior run. And we calculate the softmax probabilities for all the data set. And then we select the range of the probabilities, and we optimize over this range to get the maximum efficiency for the anomaly selection. Now I will show you how this method works, considering a typical well-known example for new physics searches in particle physics, named fat-set topologies. We consider an array of BSM searches scenarios, starting from the boosted Higgs production in effective field theories and the heavy resonance decaying into multiple channels where the fat jet will have 2, 3, or 4 subjects, coming to the input data set. For the normal standard model events, we simulate two types of data sets: standard model TT bar and QCD diejet production. We consider the leading fat jet with PT greater than 750 GeV, and the output of the detector can be seen as the 2D images, and these are the averaged images for the QCD jets, PT averaged images, and for the top jets. We feed these images to the CNN of this architecture with 4 convolution layers, and we perform the binary classification. So because these images are quite different from each other, these fat jets, we can see that the classification is quite good. These distributions are quite far from each other. And now we have this trained model on these two data sets, and we simulate the couple of BSM benchmarks, as I mentioned earlier. the graviton heavy resonance in RS models, decaying to 2, 3 or subjects, and the Higgs production. And we get the predictions for the BSM events considering the previous model trained on the normal dataset. So we can see that what this method does, model does, it tends to align the BSM examples towards one of the class on which it is trained on. So clearly it is not able to distinguish the new physics events from the standard model events or the anomaly dataset from the normal event. And then so this was the prior run, and then comes the anomaly awareness run. So what we do in this run, in addition to the normal dataset, in the training we also include the anomaly dataset. So in the first plot only the WZ, which is the another example we simulated. And so even with the presence of one type of anomalies, we can see that all other BSM anomalies are gathering towards the center of the distribution. So now on top of WZ, we also add the another type of anomaly, which is R3. So we can see that the distinction between the BSM events, anomalies, and the standard model events becomes better, and it improves further with the inclusion of more varied set of anomalies. So the awareness of varied enough set of anomalies makes it a robust anomaly detector. So, but after one point, once it learns quite well the different set of anomalies, the information saturates. So you can see that there is not much difference between these two plots, where we have here 4 type of anomalies and here 5 type of anomalies. So now how to quantify this anomaly detection? So in just for the illustration purposes, I will just talk about a specific criteria which is more relevant for the particle physics. So here we start from the window around 0.5, which is where the most of the BSM events gather. So we scan over this window. We try to choose the optimized range in order to maximize this ratio. So here epsilon s is the efficiency for the signals selection or the anomalies in the selected window, and epsilon b is the corresponding parameter for the background events, QCD and TT bar in this case, and sigma b is the background cross section. And then using this maximum value, we use typical statistical criteria S over square root b for the new physics detection to translate into a generic anomaly cross section. So here I have a cross section versus luminosity, and here we consider the EFT case, which was not the part of the training. The anomalies considered in the training. So this was the unseen anomaly. So we can see that even for the huge QCD and TT bar cross section, this method is still capable of probing the cross section of order of 10 femtobarn, so which is very interesting. So to summarize, anomaly awareness is the anomaly detection method, which is based on the classification of the normal events. And while in the process of the classification, it is made aware of the presence of the anomalies by modifying the learning function. And once the learning is complete, it is able to identify the unseen anomalies, and it could also be generalized to the normal data set having more than 2 classes. Thank you for listening. I will be happy to answer your questions.
Okay, great. Yeah, so I think we're running slightly behind, but let's take a couple questions if anybody has them.
All right, here I can ask a question. So for the first talk, I was wondering, so for Florian, I was wondering how well is the physics performance? I mean, given this large speed up? I mean, it's not clear from just this one distribution, right?
Do you mean about in the generative adversarial network in general, or about a quantized model?
Let's say in general, because, right, I mean, typically the GAN-based GEANT studies that have been done in the past work pretty well, but miss some information about the tails or some of the higher order correlations, right?
Yes, so we did a lot of research already in the past and proved already that it reaches the same level of accuracy that it is necessary for our simulations. And yes, in fact, we have some problems, or we had some problems with the tails, but also with the conversion from the 3D networks to the 2D convolutional networks. We could solve these problems, I think, because we could now also increase the number of parameters, and we have a slightly more complex network architecture. So it is good. But you're right, we cannot say just with 1 or 2 metrics, physics metrics or graphs, we cannot show if physics accuracy is good enough. So we have at least 5 more graphs, and in most of them, also the quantized tool is very well. We have just 1 graph in which the quantized model works not so well, and this is on what we are working next, that we create a new validation matrix and implement this in our ILOT quantization tool, that we can also optimize for this, and maybe then our results get even better.
Okay, great. Thank you.
Thank you.
Are there any other questions? If not, I have one for the last speaker, which is, so in the example you showed, especially when you did the sort of looking at the full sensitivity, you included, I think it was 3 sort of new BSM inputs. Have you looked at what happens if you say only include one of those? How much, what's sort of the performance hit you take, and what's the performance, conversely, what's performance gain from adding more and more BSM inputs as training for the model?
Yes, I do not have that sensitivity plot, but in the middle plot, I'm going to share my screen again. You see my screen?
Yep, I see screen and the mouse.
Yeah, so here you can see that only one is not good for all like varied set of anomalies. So you need to make it aware of the varied enough number of anomalies to make it robust against a varied unseen number of anomalies. So for example, here you do the training for WZ, but for this one, you still have, even you select the window somewhere here, you still have a lot of events in this range.
Okay, I see, yeah. Thanks. Any other questions? If not, maybe in the interest of time, we can cut it off here, since we're already about 20 minutes behind. So thank you very much to our speakers.